Hello, everyone. The purpose of this lecture is to give a little context to the last one about trig functions and simple harmonic motion. We're just going to look at an example problem where we apply this idea of trig functions, and you can see how useful they are and how easy they are to work with. Might have felt a little bit overwhelming, the stuff we did with the graphs last time, but I want you just to kind of not worry about it, and I want to show you how it works out. It's really not too bad. So here we go. Let's jump in. We've got sort of a standard problem here. We've got a mass and a spring constant. We're pulling it back 16 centimeters and letting it go. And then I just ask you this whole slew of questions, and we're going to use some trigonometry to help us figure them out. So the first thing I'm going to do is turn this word problem into a picture. So I'll draw my spring mass system and my equilibrium here, x equals 0. Put the mass out here at the end, because it's being pulled to 16 centimeters away from equilibrium. Do something, draw it out like this. So that means that its original starting position is going to be 16 centimeters. We'll go to our base metric units, 0.16 meters. My mass, again, careful with units. I'm going to divide 60 by 1,000, so we get the kilograms for my mass. And then my spring constant is already in base units, 105 newtons per meter. So now everything can be plugged into equations just like it is. So this is what this thing looks like when I first release it. Now I'm going to answer all the questions regarding this. Okay, so the first question is the amplitude. So actually no math is required here. When you pull something back a certain distance, if you release it from rest, that becomes the amplitude of oscillation. So in this case, the amplitude is just going to be the 16 centimeters. If I pulled it back 10 centimeters, then the amplitude would be 10 centimeters. Okay, so that's just kind of stating that right from the picture. Part B, what is the angular frequency? Now, be careful. I'm asking you angular frequency for B and regular frequency for C. So we've got to not mix the two up in our mind. So angular frequency, that's this new thing, omega, the rate at which my trig function repeats. And both of them are telling me how quickly the thing oscillates. One is giving me cycles per second, which is frequency. The other is giving me radians per second, which is omega. So we look at our equation card. I gave you a formula last lecture for omega. It depends on the spring constant and the mass. So it's the square root of k over m. So it's pretty easy to calculate because I'm given both of those things here. I just need to be careful that it's omega that I'm being asked to find. So we'll put in the spring constant that I gave you and the mass that I gave you in kilograms. And we'll solve for this with our calculator. It gives me 41.8 radians per second. So as this thing oscillates back and forth, it's going to vibrate through almost 42 radians every second as the trig function goes back and forth. Now, it's a little hard maybe to picture in your mind, but it's actually going to be really useful. I'm going to use that number later on in the problem. It's not maybe as visual of a number, but we'll see its usefulness as we go. Now I'm looking for the regular frequency. So regular frequency, that's just F. And there are kind of two ways that I could find that here. If I look at my 3x5 card, I have an equation for regular frequency. 1 over 2 pi square root k over m is one way that I might find that. I've got all of those numbers. I could just solve for it that way. However, since I know my angular frequency, the two are related to each other. We learned last class that omega is equal to 2 pi times the frequency. I might as well just use that. I don't even have to take a square root. In fact, you'll see that mathematically they end up being the same thing. But I'm going to use this second form right here because I've got omega, 41.8 radians per second equals 2 pi times the frequency. So then I can just divide both sides by 2 pi and find the frequency. A word of caution to you, whenever you divide by 2 pi in your calculator, it's critical that you put the 2 pi in parentheses. On the TI calculators, if you type 41.8 divided by 2 pi, what it will do is it will divide by 2 and then multiply by pi, but you want to divide by both of them, so you need to divide it by 2 pi in parentheses. If you do that correctly, you can check with your calculator and make sure that it is turning out correctly. You get 6.66, which is the frequency of the beast. Let's see, 6.66 hertz. So that's a little bit of an easier number to visualize. This thing goes through just over 6.5 vibrations back and forth every second. 6.5 times per second, that's really fast. So this is going to be kind of a blur to our eyes as this thing vibrates back and forth. All right. D, the position as a function of time. Now, this is a real powerful thing that comes out of the trig functions. I want to know not just where it is at the beginning, but at any time in its motion where this thing is. I should be able to come up with a trig function for this. And we had derived, let me just remind you of what this looks like. We had derived an equation for position as a function of time. We found that it was a cosine function. And all that I need to know is amplitude and omega. And I know those two things. I just need to plug the numbers in. Now, a word of caution about this. In our derivation, we had started at positive amplitude, which is why it was a cosine function. But these position functions, they can be just about any trig function. They could be a sine, they could be a cosine, they could be positive, they could be negative. It all depends on where you start. So if instead of starting out here at positive amplitude, if I had began at negative amplitude, then it would be a negative cosine function. Or if I had begun at equilibrium and had it moving one way or the other, it could be a positive or negative sign. So either way, it's still going to be amplitude and omega, but this trig function can vary depending on the initial condition. In this case, though, I'm beginning at positive amplitude, so it's going to be the same form that we had before. X equals A cosine omega t. So to give the answer to this question, position as a function of time, I just need to plug the numbers in. So I'm looking for position as a function of time. So A, I know to be 0.16 meters. So 0.16 meters times the cosine, and omega I know to be 41.8 radians per second as a function of time. So here's my answer for part D. And what I could do with this now is I could plug in any time t and figure out where this thing is. I could plug in 3 years from now where this thing's going to be, as long as I do it in seconds, and I'll find its position at that moment. Assumes the friction doesn't slow it down, of course. All right. Letter E, the maximum speed. Now, I could use energy conservation to correctly solve for this maximum speed, turn potential into kinetic. But I'm going to use my new trig trick, a little hard to say, trig trick, to figure that out. Since the amplitude of my velocity function, regardless of whether it's sine or cosine, the amplitude is going to be equal to A omega. It's a nice quick way of finding my maximum speed. So if I put 0.16 meters, my amplitude, times 41.8 radians per second, omega, my calculator says 6.7. 6.7 meters per second. That's my maximum speed, the fastest this thing's going to go. It's kind of a nifty, quick way of finding maximum speed. Now, some of you may be wondering about units here. Why isn't it meter? Where did the radian go? Technically, a radian isn't actually a unit. It's a ratio of arc length to radius. So it's two lengths ratio. The unit, it's a dimensionless quantity. So it's okay to just leave it out. So that's the quick answer. Part F, almost through this problem. So it's a little faster maybe than you were thinking. We're looking for maximum acceleration in G's. Oh, G's. So what's my maximum acceleration? Well, we learned a function for that from my trig functions last lecture. My maximum acceleration is equal to the amplitude times omega squared. So we can find that since we know both of those things. So my amplitude and omega, but this time it's squared. And so this thing's going to have a maximum acceleration of, wow, it's a pretty big acceleration, 280 meters per second squared is my biggest acceleration this thing's going to have. It's really going to be accelerating as it jerks back and forth. And I am asked to change that into G's. So a G is just the same as the acceleration of gravity. It's a multiple of gravity's acceleration. So this is a unit conversion that we're making here. And so I'll use my factor label. 1G is the same thing as 9.8 meters per second squared. And I'm going to put the G's in the numerator and the meters per second squared in the denominator so that the meters per second squared cancel out. So 280 divided by 9.8 is going to give me my G's of acceleration. It ends up being about 29 G's, or about 29 times the acceleration of gravity. It's a very big acceleration. Almost done. Last part of this problem, letter G. What is the position? Now I just kind of picked a time at random. What is the position after 19.5 seconds? Now this is something we couldn't do without the trig function. We couldn't use energy conservation or any other trick we know to find that. I mean, after some random amount of time, where the heck is this thing? We know it's somewhere between positive and negative amplitude, but where exactly is it? We can now find it. And that's sort of the purpose of finding this position function. We can find now the position at any time t. So let's do so. So I'm going to use my position function. X is equal to 0.16 meters times the cosine of 41.8 radians per second. I'm just using my answer from part D. But now I'm going to plug in the actual given time in seconds, 19.5 seconds. That's what I'm putting into this. And I can use my calculator then to figure out where this thing is. And it could be a positive number. It could be a negative number. It's going to be somewhere in between positive and negative 16 centimeters. Now, one important caveat about this is because I'm using radians. This is the first and only time in our course where my calculator needs to be in radian mode and not in degree mode. So for this whole unit, really, we don't do anything with degrees. It needs radian mode is where you'd want to be for a test or a quiz. But make sure your calculator is in radian mode before you put this in. And my calculator will return negative 0.023. Negative 0.023 meters, since it's a position. So it looks like at this particular time, this thing is to the left of equilibrium. And in meters, that's 2.3 centimeters. So the answer is 2.3 centimeters to the left of equilibrium, or to the left of the x equals 0 spot. So there you have it. Hopefully that's helpful. You're going to try some practice problems now and see if you can do this on your own. Use this as a model. Good luck, and please ask questions if you have any. We'll see you later.